Picture a single electron sitting in a copper wire inside your bedroom wall. It has lived in that exact wire since the day your house was built. It has never left. And yet you believe, with total confidence, that this very electron has traveled hundreds of miles from a wind turbine in the hills just to power your bedside lamp. That's utterly wrong. The electrons in your house stay in your house. They don't travel from the power plant at all. If they did, your electricity would take hours to reach you. I find it marvelous that people are happy to trust a system they fundamentally misunderstood. You flip a switch, the light comes on, and you assume a tiny particle has sprinted across the country in a fraction of a second. It hasn't. Your mental model of electricity isn't just slightly off, it's completely backwards. What actually travels from the power station isn't the electron, it's the force that pushes it. So what is really happening inside the walls of your home? Let's look at the wire itself. That copper cable hidden behind the plaster is essentially a tube packed tight with billions of free electrons. Think of them like water in a perfectly full pipe. The electrons are already there, sitting in the wire, waiting. When the generator at the power station starts turning, it doesn't send new electrons into your home, it applies pressure. The generator pushes the electrons that are already in the line. Because the wire is already packed tight, when a generator pushes an electron at the power station, it pushes one out the other end of the wire inside your house. The chain reaction is instantaneous. This pushing force is called voltage. You can think of voltage like water pressure in a plumbing system. It isn't the water itself, it's the force squeezing the water through the pipe. When you plug in your kettle, you're opening a valve. The voltage from the grid rushes through your home's wiring, pushing your local electrons forward in a wave. That wave is what powers your devices. The actual electrons, the physical particles you imagine traveling all that way, are just shuffling back and forth over incredibly tiny distances. They never leave the building. Now then, the conventional view does get one thing right. There's a genuine journey happening from the power plant to your home, but it's a journey of energy, not matter. You can think of this energy as traveling in invisible fields around the wires rather than through the copper itself. To understand how this energy makes that long trip without getting lost, we need to look at the machines that make it. I dare say the engineering involved is frightfully clever. Electricity is generated at a power plant. This could be a hydroelectric dam, a nuclear reactor, or a coal facility. They all do the same fundamental thing. They spin a magnet inside a coil of copper wire. When that magnet spins, it pushes the electrons in the wire. This creates our electrical pressure, the voltage. It's a simple mechanical process at its heart. You're just moving a magnetic field to shove particles around. But here's the hidden complication. The voltage that comes out of a power plant is actually rather weak for long-distance travel. If we tried to send that raw electricity across the country, the resistance of the wires would absorb most of the energy as heat. It would be a dreadful waste. The electricity would simply dissolve into the air before it ever reached your street. Resistance is the natural friction inside any wire. The longer the wire, the more friction you get. To defeat this friction, we've to turn the electricity into something far more aggressive before sending it on its way. We send it through a transformer. A transformer is a device that either steps the voltage up or steps it down. To push electricity across hundreds of miles of cable, we use a step-up transformer at the power plant. It takes the lower voltage from the generator and multiplies it into extraordinarily high voltage. We're talking hundreds of thousands of volts. At these extreme voltages, the electricity can force its way through the long transmission lines without losing much of its energy to friction. The invisible energy field travels at nearly the speed of light, racing across the landscape towards your town. When it gets close to a populated area, that incredibly high voltage is dangerous. It has to be tamed before it can safely enter a neighborhood. The energy passes through another set of transformers called step-down transformers. These massive machines do the exact opposite of the ones at the power plant. They take the ultra-high voltage and step it back down, reducing the pressure again and again. By the time the electricity reaches the substation near your local high street, the pressure has been lowered to a much safer level. From there, it travels along the distribution lines, which are the overhead cables you see on wooden poles or the thicker underground cables buried beneath the pavement. The voltage is reduced one final time by the small transformer sitting on the pole outside your house or in the green metal box on the corner of your estate. Finally, the electrical pressure enters your meter and your fuse box. At this point, the force is perfectly calibrated for your appliances. You're no longer dealing with the fearsome, high-pressure energy that shot across the countryside. You've a steady, manageable voltage waiting patiently in the copper wiring inside your walls. When you turn on your television, you're completing a circuit. You're giving those local electrons a path to follow. The invisible energy field from the grid pushes them, and the television lights up. The physical electrons inside the wire are just the local workforce, dutifully responding to the long-distance pressure sent from miles away. They do the actual work inside your home, but they never made the journey from the plant. So, the contrarian view is the correct one here. The conventional idea that electricity is a flowing substance traveling from a distant source is a fundamental misunderstanding. We don't consume electrons, we borrow them. The utility company doesn't sell you tiny particles, they sell you the pressure that moves particles you already have. Your home's electrical system is essentially a closed loop. The electrons simply oscillate back and forth within that loop, driven by the remote generator's push and pull. It's a beautifully efficient system. We move energy across vast distances by just pushing on a wire that's already full. When does the old conventional view still matter? If you're dealing with direct current rather than alternating current, the picture changes slightly. Direct current, or DC, is the kind of electricity you get from a battery. In a DC circuit, the electrons genuinely do drift continuously in one direction, though even then, they move terribly slowly. The actual drift speed of an electron in a battery-powered circuit is less than a millimeter per second. A snail could outrun it. Your car battery relies on chemical reactions to keep that slow march of electrons going, pushing them around a closed loop. The old water flow analogy works better for direct current because the particles are at least moving consistently in a single direction. But the electricity coming out of your wall socket is alternating current, or AC. With AC power, the generator at the plant reverses its push dozens of times per second. The electrons in your wall just jiggle back and forth in place. They go absolutely nowhere. I must say, it's a rather elegant design. By using alternating current, we can use those brilliant transformers to step the voltage up for long journeys and step it down for safe home use. You can't do that easily with direct current. So, the next time you charge your phone, spare a thought for the invisible, high-pressure field that traveled at the speed of light to reach your street. And give a nod to the loyal electrons already living in your walls. They did all the heavy lifting. Which everyday technology completely baffles you, despite using it every single day? Let me know in the comments below. If unraveling the hidden mechanics of the modern world brought you some clarity today, do give this video a generous rating to help others discover it. Pass the link to a friend who still pictures little lightning bolts rushing down the wires, and subscribe to the channel so we can untangle our next great puzzle together.